Okay, so first of all, I'm Dario, and I'm gonna talk about some analysis I did for beyond the standard model effects from the CONUS data. So first of all, what are we talking about today? Today we're talking about sevens, but since we heard already very nice words about this yesterday, I'm gonna gloss over this a little bit faster because there's not a lot of time. So it's a neutral current interaction that as we have seen, and it mainly consists of a neutrino scattering of a nucleus via a Z boson exchange. And the coherence condition is given by the fact that at low energies, low enough energies, the neutrino sees the nucleus as a unity and doesn't see the internal structure. So how do we describe this in the standard model? Well, we have a nuclear weak charge that is written down here. And very important is that it happens to scale more or less with the number of neutrons. And this brings to coherent amplification in the scattering, as we can see here. And also from kinematic effects, we can calculate the maximal recoil energy that the nucleus can have. We have also already said that if the coherence condition is met, the neutrino doesn't see the internal structure, so the form factor of the nucleus can be approximated to 1. Now, what do we need to detect such an interaction? We need, of course, a high cross-section, but since the cross-section, which is plotted here on the right, rises towards lower energies, we also need a low threshold. That is, going towards a low threshold, we get higher cross-sections. An additional experimental challenge that we have here is quenching, since what we actually detect is the ionization energy in the crystal and not directly the recoil energy of the nucleus. And through scattering with other nuclei, the nucleus loses part of this energy via this effect, and not the complete recoil energy goes into ionization. So a very important thing here is the choice of the nucleus, of the target nucleus that we should choose for such an experiment. So what do we need? We need, of course, a high cross-section, as we already said, so a high neutron number, but at the same time, we need a high maximal recoil energy. That means also a low mass. So the right choice probably lies somewhere in the middle. And for the CONUS experiment, the choice was with germanium crystals. Now, why is this interaction so interesting? First of all, it offers quite a high cross-section, especially for neutrino experiments, if compared to the huge masses of inverse beta decays, for example. Here you see the classic image of Super Kamiokande with its 50,000 tons of water, compared to the mere 4 kilograms of the CONUS detector. Also, it offers a very clean channel for new physics testing, especially beyond the standard model effects, as we will see in a moment. Here is a very short timeline of the sevens prediction and detection. It was first predicted in 74, but it would have to wait till 2017 for the first detection in the coherent experiment, and till 2025 for the first detection in a nuclear reactor by the CONUS experiment. Okay, so the CONUS experiment was located in Germany, Brockdorf, in a very powerful nuclear power plant, and was equipped with 4 1-kilogram germanium detectors, which were shielded via layered lead borated and unborated polyethylene and an active muon anti-coincidence veto to lower the background as much as possible. And there was already in the room where the experiment was situated a 24-meter overburden. And very important, the data acquisition was done both during reactor on and reactor off period, because once a year for a month, the reactor was turned off for maintenance reasons, but that offers a very important piece of information to validate the background model. This is the final sevens result of the CONUS experiment, which set at the time the best limit on sevens detection at nuclear reactors. But unfortunately, the power plant was shut down in 2021. So as we will see later, the experiment had to relocate. Now, in my analysis, what we used was a log likelihood procedure where the on and off data were fitted simultaneously with their respective parameters, and any additional information on measured quantities or systematics was included via Gaussian pool terms. Now, what kind of beyond the standard model effects are we going to talk about today? So we're going to talk about vector NSI, which stands for non-standard interaction, but also light mediators, specifically light scalars and light vectors. Why vector NSIs? They offer a relatively model-independent way to modify the standard model to include an interaction that couples neutrinos to quarks. Simply put, we add to the standard model Lagrangian an operator which couples neutrinos to quarks, and that modifies the weak nuclear charge. Here, the epsilons are typical NSI parameters, but the second line can fortunately be ignored or we ignored it, because only electron neutrinos are produced in nuclear reactors, and we assume that there's not enough time in 70 meters for them to oscillate. If we had sterile neutrinos, that would be different, but that's another story. And as you can see also, for different epsilon parameters, you can also have destructive interference. Here is a plot of the expected cross-section that we would get for different parameters. In red, you have the sevens cross-section, and yeah, of course, if we had both negative parameters, we would get a huge cross-section. That is not the case, unfortunately. So this is the final result of the analysis. This is an inclusion plot. That means that the shaded areas are the allowed areas in the plot, where we have on the x-axis the epsilon parameter for the down quark, and on the y-axis for the up quark. And as you can see, it's quite competitive comparing to other experiments such as Texono and Coherent. Coherent gets 2 bands instead of 1 because they actually see the 7 signal that we still didn't see in the run 5 of CONUS. And that is because of a degeneracy in the weak charge. If you want, we can talk a bit more about that if you have questions. But okay, a plot as the one that I just showed is kind of hard to interpret. So a much better way to see it is that we specified the model only at the low energies, so it was an effective field theory. But if we were to specify it at high energies, we would get a vector mediator that mediates the interaction. And through the estimation of a limit on epsilon, we could also estimate the sensitivity to this new mediator. And what we get is around 140 GeVs, which, considering that the experiment has neutrinos of the order of a few MeVs, is quite impressive, I think. Now, another way that we can modify the standard model, well, actually, I think the simplest way we can modify the standard model is just by introducing a new U1 gauged CP-even gauge boson, scalar boson, phi, or a scalar or a vector boson, Z, as we can we'll see later, that simply couples to quarks, electrons, and neutrinos. Here, universal couplings are assumed for simplicity. So the coupling of the new scalar to quarks, electrons, and neutrinos is the same. Here is the predicted cross-section that we get. So as you can see, there is no destructive interference. So the signature of such an interaction would just be a surplus in events. Sorry. What do I have to do?
Okay, we saved it. Yes, well, okay.
On, off.
Don't press it now. Okay. I think we have to wait until
I can go on.
Yes. Maybe you try to fit. I think this was almost the last slide, right?
Yeah. Oh, 2 slides.
Yeah.
Okay, so very fast. Yeah, the results that we get is a plot that you will see in a second.
The tension is building.
Right? Wow, okay. Very nice plot. No. This is an exclusion plot. So the allowed area is the white under. And as you can see also here, it's quite competitive comparing to the other experiments. Only thing to note is that, for example, Panda X, Xenonton, and LZ, and Vorexino are electron scattering experiments. So not sevens. So they have better sensitivities for lower masses. The same can be done for the vector case. Here we consider 2 different types of coupling, one the universal and one the B minus L coupling, and cross-section is still the same, more or less. And here is the final exclusion plot that we get for the universal coupling and for the B minus L coupling. Okay, I'm gonna wrap this up very quickly because the next phase of the experiment is already underway. That is the CONUS Plus experiment, which had to relocate to Switzerland. As I said earlier, the reactor in Germany was closed off. And run 1 was still done with 4 1-kilogram detectors, but with an improved threshold of around 160 EVs. And that led to the first detection of sevens from nuclear reactors. This already triggered some phenomenology studies on beyond the standard model effects, but we believe that our investigation will hopefully put better limits since we have the full knowledge of the model and the data. And lastly, run 2 is ongoing right now with an improved mass of the detectors and backup. That's it.
Thank you, Dario. Sorry for the hiccup there.
It's my fault.
So I have a question. So you had this one of the result plots. So you have like this kink there in some of these. But is this because you had like a weak signal there, and so the limit gets worse?
This is because we had a region of interest between 210 and 1000 EVs. And towards the higher energy, we're sensitive also to electron scattering.
Okay.
So if we had only sevens, we would see just a flat line towards lower masses. But lower masses give better sensitivities for electron scattering.
Okay.
So this was included in the analysis, and that is why you see
it's different channels. Okay.
Yeah.
Thank you. Okay, I don't see any other hands, so let's thank Dario again.